Hello, everyone. This is the lecture for section 4.4, the mean value theorem. So we're going to continue in our study of applications of the derivative. One of the most heavy-hitting theorems in math, not only at our level, at this level, but in higher math. Like whenever we want to prove something even more far-fetched, even more out there than usual, right? More often than not, this is one of the theorems that is used to justify some of the steps, the mean value theorem, okay? So the idea behind these theorems, there's going to be two big ones. Rolle's theorem is the first one, and the mean value theorem is the second one down below. The overall idea of all of these theorems really make a lot of sense if you draw a picture. So if you don't understand the words that's coming, that's sort of printed down, just really remember the picture. So let me get into that so you guys can see what I'm talking about. So the first thing I want to define is Rolle's theorem, okay? So Rolle's theorem states this, right? That f has to be a continuous function over a closed interval, right? With this condition, that f of a has to be equal to f of b, okay? Then there exists at least one value c in AB such that f prime of c is equal to 0. Okay, so let me go ahead and scroll up so I can get the whole box here so I can draw. So again, like I said, I like pictures. And if you understand the picture for this one, right, the rest should just sort of fall into place. Y and X. So the first thing I'm going to do is I'm going to try to draw a continuous function over a closed interval AB, and that's differentiable. That's going to basically mean that you can take the derivative of it, okay? Over an open interval AB, such that f of A is equal to f of B. So I get to, I'm going to first go ahead and call my A and my B. So this is my A, and this is my B, right? So I'm going to go ahead and draw a squiggle. It doesn't matter what it is, but hopefully I did this about right, that the endpoint, so right here, both of those are equal. So this is the point where it is f of A, whoops, is equal to f of B. So they end up sort of falling on the same line, right? So they end up starting and ending at the same height, okay? Then what this theorem states, basically, is that there exists at least one value in AB, somewhere in there, somewhere in AB, there exists at least one value such that f prime of c is equal to 0. So f prime of c means that the slope of the tangent line, right, or the instantaneous rate of change has to be equal to 0. And lo and behold, at least for the example I drew, there's a bunch of them. There's all of these, right? And notice that all of these, the slope of the tangent line for each one is equal to 0. That's it. It is equal to 0. Okay. So that's, again, like I said, that's what a theorem is. A theorem is sort of like a guaranteed consequence. So we are guaranteed that there is at least one point, right, where the derivative is equal to 0. Okay. So to sort of show that off a little bit, okay, I'm going to go ahead and do this problem right here. Okay. I'm not going to graph it. We'll graph it at the end. Okay. So you guys can see what's going on. Okay. But we're going to verify that the function f of x is equal to that and that and that over -3/2, 0 satisfies the hypothesis and consequence of Rolle's theorem. Okay, so the hypothesis here, I'm going to do this, hype, HYP. So I'm going to first verify the hypothesis, right? So f is continuous over a closed interval over AB, and that it's differentiable, and that f of A is equal to f of B. So if you take a look at the function itself, the only value that we cannot plug in where it would be discontinuous would be at x equal -2. We plug in x equal -2, we get a divide by 0. That can't happen. So I'm going to write here x cannot equal -2, right? It's continuous everywhere else. Okay, so it's continuous. We know we could take the derivative of it. The last thing we need to check is that f of a is equal to f of b. Okay, so f of a, we're going to go ahead and f of -3/2 is going to be equal to -3. Ooh. Let's try that again, shall we? Over 2 squared minus 2, -3/2 minus 7, all over -3/2 plus 2. Okay, and what we get here is 9/4 plus 3 minus 7, all over, what is that going to be? -3/2 plus 2, so it's going to be a +1/2. Okay, if you do this all right, you should get that this should be -7/2. Okay. If we do f of 0, we get 0 squared minus 2 times 0 minus 7 over 0 plus 2. You can see all this is going to be -7/2. We're good to go. Okay, so this is a hypothesis. Okay, we just checked that. I'm going to put it down here. F of -3/2 is equal to f of 0. So we just checked the hypothesis. We just checked the hypothesis for this equation, for Rolle's theorem. Now we get to check Rolle's theorem. Now we get to check Rolle's theorem, the consequence. So now I'm going to put over here the consequence, right? This is telling me the consequence basically says, therefore, f prime of c is equal to 0. We can find a value c where it is equal to 0. So let's go ahead and try to compute that out. So we have a high and we have a low. Okay, so I'm going to skip a couple steps. F prime of x is equal to low x plus 2. D high, that's going to be 2x plus 2 minus high x squared minus 2x minus 7 d low times 1 all over the bottom squared, x plus 2 quantity squared. Okay. If you simplify this all out, what you're going to get is x squared plus 4x plus 3 all over x plus 2 quantity squared. So we have a derivative, right? We are now going to find where f prime of x is equal to 0. So that means x squared plus 4x plus 3 over x plus 2 squared has to be equal to 0. From the previous section, we know that if we have a fraction is equal to 0, that means the very top is equal to 0. So x squared plus 4x plus 3 must equal 0. And if you guys remember how to factor this out, this is going to be a x plus 1, x plus 3 equals 0. So then therefore, right, x has to be equal to -1, or x has to be equal to -3. Got it? And we are done. And here's why. The consequence of Rolle's theorem says that we are guaranteed a value inside here. We are guaranteed a value inside of -3, 2, 0. So within that interval, we're guaranteed a value in there where the derivative of our function is equal to 0. And we got down to this point right here. So either x has to be equal to -1, or x has to be equal to -3. -3 doesn't live in the interval, -1 does. So I'm going to go ahead and go scritchy scratch this one. That one's not it. It's this one over here. So then we have there exists x equal -1 such that f prime of -1 is equal to 0. There is our consequence for Rolle's theorem, okay? So this is verifying that the function satisfies the hypothesis and the consequence of Rolle's theorem. So now let's, for kicks and giggles, let's go ahead and verify this. So what I'm going to do is I'm going to do a split screen here. Okay, I'm going to open up the tangent line calculator. Okay, and I'm going to put in my function, which is that one right there, x squared minus 2x minus 7, right? Divided by, not that, well, not all of it at least. That thing divided by x plus 2. So here it is. Here's our function, right? It's a little double swoosh, okay? Between -3, 3/2, 0, that's about between maybe like what, right here? No, sorry. -0.5, about right here to 0, right? So apparently, if we plug in x equal -1, we should get a derivative of 0. We should get a tangent line with a slope 0 there. So let's go ahead and move it down to -1. And lo and behold, there's our line. Okay. So it works out. Okay. The next thing that comes up now is quick checks. I just want you to verify the hypothesis and consequence of the Rolle's theorem, just like I did before in the example above. Take it, step by step. Do the hypothesis first and do the consequence next. Okay. Make sure that you justify continuity appropriately. Okay. That might mean that you need to go back to the previous sections to make sure that you're doing it right. Okay. So now comes the next one. This is the more important of all the theorems that happen in math. Okay, the mean value theorem. Okay, so let me read it out first. Let f be continuous over a closed bounded interval and differentiable over that same interval AB. Okay, then there exists at least one point C in AB such that f prime of C is equal to f of B minus f of A all over B minus A. Okay, this one needs a little bit more dissection, but it's similar to the Rolle's theorem. Okay, notice that in this one, there's no condition about the values being equal, right? About the endpoints being equal. Okay, this one has no requirement there. The way that I like to describe this, okay, to make it make a little bit more sense is this. That, and I'm gonna write it in this. Let me do this pink, and there we go. So I'm gonna write it this way. Of f at x equals c. That's what the left-hand side of this equation means. Okay, that we're taking the derivative of f at a specific point c. Okay, And this other side, this should look familiar. It looks like a slope, and it is. It's the slope between the endpoints. So that's what this other portion means, the right-hand side. The right-hand side basically means slope between the endpoints, okay? So let me now draw a picture of what this means, okay? You guys can see maybe that there's a sort of like it's similar to Rolle's theorem, but not exactly. It's a little bit more, it's a little bit more general in this case, okay? So I'm gonna go ahead and draw the X and the Y. Whoa, my hand slipped there. All right, here's my Y-axis and my X-axis, right? So I'm gonna just draw a good old squiggle. Okay, I'm gonna go and then stop right there. So here are my two endpoints right here. There's this point right here, and this point way up here. So this is gonna be my A, and this way over here is gonna be my B. Okay. So the first thing I'm going to do is I'm going to stick in the right-hand side, okay? The right-hand side dictates that I get to draw a line between these 2 points. I'm going to draw them as best as possible, like that. There we go. So this value right here, this is going to be my M is equal to the F of B minus F of A all over B minus A. This line has a slope of F of B minus F of A all over B minus A. Okay. From the mean value theorem, it says that we are guaranteed at least one value, that value being a point C, right? Such that when we take the derivative of our function at that value C has the same slope as this line. Okay. Basically saying, let me write this in, right? That we are guaranteed at least one point. Okay, in this case, the way I have it drawn, there's maybe 3. There's one right there. There's one right there. And there's maybe one maybe right there, about where the slope of the line right there. The derivative is parallel to that pink line right there. We are guaranteed at least one of these. We're guaranteed at least one. So this can be the value C. This can be the value C. This can be the value C. We're guaranteed at least one value where the derivative at that point is equal to the slope between the endpoints. That's what it's basically saying. Okay. So I'm going to go ahead and do this just like we did before. I'm going to verify, and then we'll double check it just so that we can make sure. Okay. We're going to verify that this function over those two values right there satisfies the hypothesis and the consequence of the mean value thing. Okay. So first things first, I'm going to do hypothesis, all right? So if you guys remember, right, x and cosine of x are continuous, right? So therefore, f of x is continuous. That's it. We just satisfied continuity, right? If you guys remember back when we were talking about continuity, if you have two continuous functions and you add them together, that thing must be continuous. We're done here. So thankfully, for mean value theorem, we're done with the hypothesis. Okay, so now comes the consequence. And that's what we're going to do here. Okay, we need to check this thing. F prime of C is equal to F of B minus f of a all over b minus a. So what I'm going to do first, okay, and it's got to be over negative 5 pi over 6, comma 7 pi over 6, okay? Okay, so what I'm going to do first is I'm going to compute the right-hand side of the equation. I'm just going to find the slope of the tangent line. So I'm going to do f of 7 pi over 6 minus f of minus 5 pi over 6 all over 7 pi over 6 minus 5 pi over 6, minus a minus. Let me change that really quick before I mess it up. Minus a minus. Okay, and we're off to the races. So this is going to be 7 pi over 6 minus 2 cosine of 7 pi over 6 minus minus 5 pi over 6 minus 2 cosine of minus 5 pi over 6 all over. I'm just going to reduce the bottom automatically. This should be 12 pi over 6. Okay. If you do all this right, you're going to get 7 pi over 6 plus 5 pi over 6 all over 12 pi over 6. So the top is the top and the bottom is the bottom. And this is all going to be equal to 1. So we found the slope of our endpoints, the slope of the line between the two endpoints, and that slope is 1. Okay. So according to mean value theorem, there's got to be a value in here where if we take the derivative and plug in our c value, it's got to be equal to 1. Okay, so now we get to find the left-hand side of this equation that's right here. Okay, so I'm going to go ahead and do f prime of x. I need to take the derivative of the original, so that's going to be 1, right? Derivative of cosine is negative sine, so it's going to be plus 2 sine of x. Okay, and we want this equal to 1. Okay, that is sort of like the consequence of the mean value theorem, right? Okay, so we get to solve just this portion right here. We get to solve this out. So then therefore, right, 2 sine of x is equal to 0. The only time this happens, right, is when sine of x is equal to 0. And the only time that happens is x is 0, pi, 2 pi, 3 pi, dot, 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 dot. Okay, cool. Now, the idea is it had to live in here, right? The only two that do live in there are the first two. 2 pi is too far, and 3 pi is too far. So there we go. So by mean value theorem, we do MBT and BT, right, are guaranteed are these two values right there, 0 and pi. Okay, So now what I'm going to do is I'm actually going to verify this. Okay. And the way that I'm going to do that is, again, by Desmos. So I'm going to go ahead and open up my handy dandy trig thing. And I'm going to do a split screen again, half and half. Okay. I'm going to put in the original function. So x minus 2 cosine of x. Okay. Let me zoom out a little bit so you guys can see how wonky this thing looks. It's basically a squiggle that continues to climb. Okay. And I'm going to go ahead and change the settings for it so I can do the steps basically so the tick marks can show up. I'm going to do them by pi over 6. Hopefully you guys see what I'm doing there. So now everything, all the tick marks that are showing up are in pi's, right? Okay, so then now, this is saying that the slope of our tangent line, or sorry, the slope between our endpoints, the slope between the points about right here, negative pi over 6, and let me go ahead and squish this a little bit. So let me do negative 10 to 10. This is much easier to do if you're on a tablet. So from pi over 6, so this point right here, so this point up here, the slope there is 1, which makes sense because it's the very top of a squiggle to the very top of a squiggle. They should be differing by about, okay? According to mean value theorem, there are 2 values. These 2 values right here, 0 and pi, where the slope is equal to 1. Okay, so I'm going to open up this thing again, and I'm going to go ahead and, instead of having it as negative 1 there, I'm going to actually type in 0. And if you guys take a look, there is the slope of our tangent line is 1 there, right? And then let's go ahead and type in pi now. The slope there is also 1. So both of those points, right, satisfy the consequence of mean value theorem. All right. I believe that is it for this section. We are done after this, isn't it? Let's see. Yep, lecture questions. Cool. Just keep in mind, like, go through the steps just like I did. It'll help you guys out in sort of organizing your thoughts, making sure you don't get lost while computing stuff out. Okay. If there's any questions, please send me an email, drop into my office hours in the math lab or in my Zoom room. I'm in there every day from 3 to about 6 o'clock in the afternoon. Besides that, hope to see you guys around.